Hi. So we've covered a lot in the videos so far. The big ideas, the instruction buffer, register renaming, and we've seen a concrete implementation of how we might achieve dynamic scheduling with Tomasulo's algorithm and organization. To help make some of those concepts concrete, I ran through an example of how 6 instructions would run on a Tomasulo microarchitecture. We saw many of the details of how the various data structures in Tomasulo's organization are used. But maybe you felt a little bit cheated. Dynamic scheduling, after all, prefers a large instruction scope to find many independent instructions to play with so it can reorder execution to improve performance. But that example covered a mere 6 instructions, and it took 58 cycles to run them. So, in this video, I want to redeem myself and give you an example of dynamic scheduling on a much larger instruction scope. And to do this, we will look at dynamic scheduling as loop unrolling. I mentioned loop unrolling as an example of static instruction scheduling, so reordering instructions using information we only have at compile or development time. So loop unrolling consists of 3 main steps. In the first step, we combine the iterations of the loop, and the purpose here is to increase, or this increases, the scheduling scope, the number of instructions that we have to play around with. So the larger the scope, the more flexibility we have in deriving more efficient, higher performance, lower latency instruction schedules. So now we have a larger scope. In step 2, we do some pipeline scheduling. Either the programmer will manually do this, or the compiler might leverage some static knowledge of particular instruction latencies. And the idea is to rearrange instructions to reduce the impact of read after write hazards. So in that in-order pipeline that we saw in the last module, we could try to mask the cost, the stall penalty of a load-to-use hazard, for example, by moving instructions that don't depend on some load in between the load and its use. And then the load-to-use stall penalty, it doesn't manifest. Okay, so we've increased the instruction scope and we've reordered instructions to come up with a more rapid issue schedule. We may have introduced some write after read or write after write violations by instruction reordering. So step 3, loop unrolling, performs register renaming to remove write after read and write after write violations that come from scheduling. So at the highest level, that's the idea of loop unrolling as a static optimization to improve the instruction schedule. And what we'll see in this video, in this example, is how Tomasulo's algorithm achieves these same 3 benefits as loop unrolling. So let me introduce our new sample program. Of course, we need a program to motivate our innovative architectural ideas. So we will be looking at a loop-based program in this example, in contrast to the 6 instructions that we saw in the last video. This application kernel is called SAXP. In particular, we're looking at SAX. So that's single precision A times X. This is a simplification of SAXP, which is single precision A times X plus Y, a commonly used linear algebra routine in many scientific workloads. We focus on SAX only because there won't be room in the diagrams below for the full SAXP. Okay, so the key idea is to multiply every element of a vector x times a constant a and hold that in another vector called z. We have the C code above and the 5 assembly instructions that would make up this loop, where the 0th instruction here is the target of the branch instruction at the end there. The R1 register holds the value of I starting at the length of both of these arrays, these vectors. Now, before we dive into the hardware, I just want you to reflect for a moment about static loop unrolling for this simple kernel and say we're unrolling by 2 loop iterations. So I have the code here for the combined double loop iteration. First a load, a multiply, a store, a subtract to update the indexing variable. And notice there's no branch. This was a key point of combining the 2 loop iterations to limit the number of dependencies, including control dependencies. And then of course we follow the second part of this combined iteration, load, multiply, store. So given these 7 instructions, how would you, the expert assembly programming hacker, reorder these instructions to respect the raw hazards, but improve performance, reduce the number of stall penalties in an in-order execute pipeline? So I want you to think about that for just a couple seconds and pause here. And welcome back. So we have some assumptions listed here below. Maybe I should have mentioned that beforehand, but some key things to note. So we have a read after write dependence from the load to the multiply and from the multiply to the store, and a similar pattern for the later load, multiply, and store. And so given the 4-cycle latency of the multiply, why should we stall the entire pipeline waiting until we can start the first store instruction, when instead, maybe we could hoist some of the independent instructions into the middle? Now, I'm not claiming to come up with the optimal schedule here, and you can do that in your own time, but we might want to hoist some independent instructions between the multiply and the subtract to mask the stall penalty. And this is the kind of instruction reordering that we hope to see on the fly implemented by Tomasulo's algorithm. So before we get into the hardware, just to reiterate these assumptions. So multiplies will take 4 clock cycles, And we assume that the first load, it misses in the cache, at least the first level cache. So it will take 8 clock cycles. But because the data being loaded in the second iteration is on the same cache line, we're going to assume the second load takes only 1 clock cycle. It has a hit. So this is only after the first load has finished executing. And this is exploiting spatial locality, something we'll cover in more detail in the caches module. Again, we're assuming that the register name R1 holds the length of the arrays, so it has an initial value of 80. And for convenience, although the program above says that Z and X are different arrays, for convenience of this example, I'm going to assume that, in fact, the destination array is the same. Okay, in the rest of this video, we are going to see how this program would execute on a Tomasulo microarchitecture. I hope you remember these data structures that we saw in the previous video. Our goal is to fill out this instruction status table, or the new version of the pipeline diagram that we've developed now that we're dealing with more complex out-of-order execution. And this register status table is equivalent to the map table that we saw before. Excellent, so let's get started with this second example, where we'll see the impact of a larger instruction scope and some more examples of how this pipeline uses register renaming to eliminate write after read and write after write hazards. So our instruction fetch queue is full of instructions. We're assuming that that's taken care of. And we are in cycle 1. In the dispatch stage, we pop the load instruction seen here. Step 1, we must allocate a reservation station entry or otherwise stall due to the threshold hazard, but we have plenty of load reservation stations available, so we will mark this first one as busy. And this instruction reads register R1. So we refer to the map table or the register status table here, and we see that its tag is empty. So we copy the data from the register file directly. And if you remember, R1 is initialized to 80. And so we copy that into the address field. And finally, the instruction writes to register F0. So we need to update the mapping so that future readers of F0 can find the correct location of this data. So we set the tag to the reservation station number of the instruction that will produce this value named F0. And this register renaming is important. We have a write after write hazard on F0. So hopefully this register status table and this algorithm will take care of that to ensure that the instructions that read the first load's value of F0 get that value, whereas readers of the second load get the correct value there as well. We'll see what happens. And moving on to cycle 2. First, let's check in on that load. It's in the issue stage now, but the key question is, can it issue? Well, all of its operands are available. We know what address to load. And so yes, in cycle 2, this load issues. It is sent to start its data cache access. I'll cover those in more detail in the next module. And checking in on the dispatch stage, we pop another instruction from the fetch queue and find the multiply. So we need to allocate a reservation station. We have one available, this mult1 station. So we allocate it and copy the opcode into the relevant field. And the instruction reads F0 and F2, so we look to the map table to identify the location of these named registers. We have a tag for F0 of load 1, which we copy into the first tag field of this reservation station entry. And meanwhile, the map table for F2 has an empty tag, meaning the data is ready, and so we copy the data from the register file, indexed by the name F2. This instruction writes to F4, so we need to update the map table. So we set its tag to the reservation station entry that will produce the value. And so just a quick refresher from the last video, notice that we have encoded this read after write data dependence on F0 through this tag system. So the microarchitecture has implicitly identified the arc over which data flows from the producer instruction to the consumer, all through these tags. Great, so moving on. We're in cycle 3. Now let's check in on that first load. It's a long latency load, it's a cache miss. It'll take 8 cycles, so we won't hear from it until cycle 10. The multiply, it can't issue because it is waiting for this raw hazard to resolve. So checking in on the dispatch stage, we have popped this store instruction. So we allocate a reservation station entry for it. The store reads 2 values, R1 for its address, which has a empty tag, telling us to copy the data from the location directly in the register file. So we copy that value of 80, address 80 that we saw for the load as well. And the store also reads register F4. So querying the map table, we see a tag of mult1 will produce the value we need for F4. So we copy that tag into the store's reservation station entry. So this is a nice spot to make the observation that renaming sets up a data flow graph. So this is a graph where each vertex is an instruction and every edge between 2 instructions represents a true data dependence, the flow of some data. The key insight of data flow execution is that an instruction starts execution when its data is available. And we can see this concept in action here. The store instruction has some of its data available, the address, but it is waiting on the Molt1 reservation station. Moving on to cycle 4. That load is still in the execute stage, and there's now a chain of data dependencies from the load to the multiply to the store. So we have no updates in the execute or issue stages, and at dispatch, we pop the subtract instruction. We allocate a reservation station in the integer add unit with an operation of subtract with an immediate. The instruction reads R1, which again has an empty tag, so we copy the value from the register file directly, which has that value of 80 that we've seen. It also reads an immediate value of 4, and so I'll put that into the VK field here, the second operand. So both of the tags in the reservation station entry, QJ, QK, they remain empty. The values are ready. Now last but not least, the subtract instruction writes as well to register 4, so we need to now update the map table so that later readers of R1 know what location will hold the correct value for R1 going forward. So we point them to this reservation station entry through the tag, setting the tag to add1. And that concludes dispatch. So moving on to cycle 5. That load is executing, the multiply and the store are waiting on operands, but the subtract is ready. Its operands are all available, so it can issue in cycle 5. We send it down to the integer ALU, and over in the dispatch stage, we pop an instruction, and this time a branch instruction. Now, step 1 has conventionally been to allocate a reservation station entry, and the handling here of the branch is partly up for debate. Some branch instructions perform some integer computation, and so would be sent to the integer ALU, and that's the approach taken in the textbook in chapter 3.4.1. Now, because the set of integer operations for branches could be simpler than a generic integer ALU, maybe we have a separate functional unit dedicated to branches, and therefore a separate reservation station for it. Or maybe we handle such simple branches, like in this example, that simply check whether a value is equal to 0, further simplifying the pipeline pathway for branches. There are several design options just for which reservation station to use here, not to mention involving real branch prediction, outcome tracking, BTBs, etc., which we will deal with in the next module. So how will we treat branches here? Let's assume there is a simplified execute pathway with a reservation station that I haven't shown in any of these tables for the sake of space. And so I will mark the branch instruction as dispatched here in cycle 5. Now, before we move on, I want to do some foreshadowing for the next cycle. Notice that we encounter the second load in the next cycle. So we're assuming a perfect BTB and branch predictor for now. So here is something concerning about that load. It is going to write to register name F0. This is a write after write dependence with that first load. And notice that the value for register F0 has not even been written back to the register file yet. So what's going to happen here? Are we going to clobber that tag? We'll see shortly. So cycle 6, here we come. So we have some complex things going on now. Let's start with the simple cases. Of course, those first 3 instructions, they're still all held up for the same reasons we saw before. The subtract, it issued in the last cycle, so it starts its execution now. Can the branch instruction issue to learn of the actual outcome? Well, no, it is data dependent on register R1. And so that brings us to the second load instruction. So we're in dispatch, and we pop this load. We need to allocate storage as usual. So we allocate this load reservation station entry. The load reads R1, which has a non-empty tag of add1, so we copy that to the tag entry. And of course, the load writes to F0, and our protocol for Tomasulo's algorithm says we simply update the map table with this, the latest writer, the most recent writer of that register name. So we simply update the mapping. But looking back at cycle 5, notice that we overwrote this tag of load 1 with load 2. So we just overwrote the tag of L1, meaning that F0 in the register file will never get the result of the instruction in the load 1 reservation station entry. The value of that first load will never make it to the register file. Now, is this concerning? Well, actually, no, it's okay. And this is because the dependent instruction on that first load, on that first version of F0, which is the first multiply instruction, it will get its value directly from the load 1 tag via the common data bus. This is exactly why reservation station entries hold the tag of the value they require, because the register file may never actually hold this version of the register name. Excellent. So we avoided the write after write hazard on F0 because of register renaming. So that is dispatch of the load instruction at cycle 6. Okay, so there's one more elephant in the room, and it's that branch. And I've talked about assuming perfect branch prediction just for the sake of getting us to cycle 6. But let's come back to reality for a moment. The branch prediction might be wrong. Maybe we've hit the end of the loop and this load instruction should not be executed. Now, I feel comfortable having dispatched the load instruction. We haven't changed any architectural state yet. We haven't updated the register file just by dispatching. But let's think about how we'll actually handle this branch. With branches, we have two options on how to handle them. First, we could opt for no control speculation. So we would impose a rule that the branch must be resolved before any younger instruction can execute. But that adds delay in the issue stage for all the instructions that follow a branch. So, of course, for performance, we prefer something more aggressive using speculation, but we must have a way to undo a misspeculation. Remember that there are three parts of any speculation. You make a guess, you have a means to detect when that guess is wrong. So in the case of branch prediction, we need to watch for the actual outcome of a branch, and then we need a means to recover in case the guess was wrong. Now in the in-order 5-stage pipeline, recovery from misspeculation was straightforward because instructions following a misspeculated branch were in the fetch or decode stage, so we simply flushed them. But in this out-of-order pipeline, we might have instructions after a branch that are executing, that are possibly writing to memory, and in the write-back stage, broadcasting on the CDB. There's complexity here on how we're going to handle that, but we will come back to these ideas later in the lecture note section 5. So in our running example in this video, we're going to pick the first option of no speculation and assuming that the branch must be resolved before the younger instructions can execute. So we'll see that in action in this video. And a little foreshadowing for your coming assignments. In Lab 3, you will be modeling Tomasulo's algorithm. And to avoid dealing with these complexities, you will assume perfect branch prediction because you developed awesome branch predictors for Lab 2. Okay, so let's move on to cycle 7 now. Okay, those first three instructions, they're held up for the same reasons we keep seeing. The load is still executing, and the multiply and store form a chain of dependencies. Now we've reached the write back of the subtract instruction because it's a simple single cycle operation. So we want access to the CDB. There's not a structural hazard. It's not in use by any other instruction concurrently. And so the CDB broadcasts the tag of this instruction and its value. So it was 80 minus 4, so it's broadcasting a value of 76. As we saw in the last video, there are two key structures that are listening for tag matches on the CDB. First is the register file. And if you refer to cycle 6 above, you'd see that there was a tag match on add 1 here. So we update the value of R1 in the register file with 76. And over in the reservation stations, we would get a tag match on add 1 in the load 2 entry. So this value from the CDB of 76 would have been copied into both the register file and this load 2 entry in the reservation station. Last but not least, the branch instruction, its reservation station is not shown, but it also would have had a tag match on add 1. It's waiting for this value as well, so that branch would receive its value. So that wraps up the write back of the subtract instruction. Assuming the CDB broadcast and tag matching happens in the first half of the cycle, like we saw in the previous video, then the branch instruction now has the data for all of its operands, its only operand. So the branch can now issue. And moving down the set of instructions, what about that second load instruction? Well, its operands are now available, so one would think we would be able to issue the load right now, but remember that rule we established in cycle 6. We are assuming there is no control speculation here, that the younger instructions relative to a branch must wait until the branch resolves before they can issue. So that's why we're not issuing the load. And so that brings us to dispatch stage. We have a new multiply instruction coming out. So let's dispatch that multiply. We allocate a reservation station entry and copy the opcode there. It reads F0 and F2. So we need to copy the tag into the tag field in the reservation station entry, but F2, its tag is empty, so that data is ready in the register file, and so we copy it into the second operand value field. And finally, the instruction writes F4, so we have to update the mapping for later readers of F4, so we point the tag to this entry of the reservation station mult2. And this is a nice point to observe that the register file is decoupled from the computation. And consequently, we are overlapping iterations. So the first and the second iterations of this loop are now overlapping. Over the course of these 7 cycles, we have started to dispatch not only the first iteration, but the second iteration as well. We're not overlapping all of the execute yet, but it's quite promising that we have overlapped several of the stages of these 2 loops right now. Now we can see this register file decoupling in action by looking at the first operand of these 2 multiply instructions. These are both reading the register name R0, but because of register renaming, their tags can track which version each of these multiplies actually wants to consume. On to cycle 8. Those first 3 instructions are still held up for the same reasons we saw before, but that branch issued last cycle, so it starts and finishes its execution in cycle 8. And as we saw in cycle 7, the loads operand is ready. We're only waiting on that branch instruction, and so this second load instruction, it can issue now in cycle 8 because the branch is resolved in the execute stage. So we'll assume that the logic for determining the outcome of the branch is so simple, we can identify early in the execute stage whether the branch was taken or not, so that over in the issue stage, by the end of the cycle, we can in fact issue the load. So it's because the load is not speculative anymore. So the load issues in cycle 8, we send it down to the data cache and or the load store queue, and this issue delay, this waiting, it was unfortunate, and so don't worry, we will add speculation, control speculation, later in the next set of videos. Our second multiply instruction, it can't issue, it's waiting for one of its operands, and so over in dispatch, we pop this store instruction from the instruction fetch queue. So let's get to work on that. We have to allocate storage, so we do so there. The store reads 2 registers, R1, its tag is empty, so we copied the value from the register file, which was written back recently and has a value of 76. The store also reads F4. Its tag is not empty. It points to mult2, which will be the producer of this value. So we copy that tag into the reservation station field so that we are listening to the CDB when it broadcasts the value that we need. And that's it for the store dispatch. So on to cycle 9. The branch instruction wrapped up its execute last cycle, so it enters right back. Now, the branch doesn't actually write to any registers, so it has no use in the CDB. It won't write to the register file or any reservation stations. In cycle 8, we basically used some sort of bypassing to enable the load instruction to issue as soon as the outcome of the branch was known in execute. Looking to that second load, it has started its execute. Now, in the assumptions above, I said that the load would take only 1 cycle on a cache hit, so it's tempting to write that execute finishes in cycle 9, but in fact we'll only get a cache hit once the first load has finished, fully finished, bringing in the data due to its cache miss. So this second load is still executing. The second multiply, second store, they're also waiting in issue just like the first multiply and store. Similar reasons, they're waiting on those loads. So let's continue this example even further, even sort of past this store instruction, and assume the loop is repeating and repeating. And so in fact, in this cycle, the second subtract I instruction is dispatched, which is not shown. As you can tell, I'm running out of space in my number of instructions here, so I hope you can imagine a sequence of instructions continuing on in this repetitive pattern here. So what does that dispatch involve? We allocate a reservation station entry and copy in its operation. As we saw before, it reads R1 and writes R1. R1 tag is empty right now, so the dispatch stage copies the value of R1 from the register file, which is 76, and extracts the immediate value of 4 from the instruction. And this second subtract instruction writes to R1 as well, so we update the map table. So we point to the reservation station in the tag field. Onward to cycle 10. Good news, that first load that had the cache miss, it's finally done its 8-cycle operation. So the first load is completing its execution, and that's in cycle 10. Now before we get to the write back, once we lose some of these tags in the current state, I want you to think about who is waiting on this load 1 tag. So who will get a tag match in cycle 11's write back? So we can see that the mult1 entry of the reservation station will get a tag match, but interestingly, the tag in the map table now points to load 2. So I had pointed this out earlier. F0 in the register file will never actually see this value loaded from memory. It's sent directly to the instruction, the multiply, that's waiting for it. Okay, and the other news in this cycle is that the second branch is dispatched, which is not shown, running out of space. So So on to cycle 11, we have some excitement, care of that load 1. So it's entered its write back, the CDB is available, so we broadcast the tag of load 1 and its value, which we'll call memory at 80. And where do we get a tag match for load 1? Well, as we saw before, it would have been on QJ, now it's erased, because we're copying in the value from the CDB, clearing the tag to mark that all of the operands are now ready for the multiply. No one in the register file is waiting for load 1. And finally, we deallocate the entry in the reservation station, and that is the write back of the load. And over in the issue stage, the multiply, the first multiply, all of its operands are now available. So by the second half of the cycle, the issue stage realizes it's time to issue the multiply instruction, send it down to that functional unit. And taking a note of what I had just said, so load 1 puts its results on the CDB, and the value from the CDB is written into VJ for mult1. The first store instruction, it's still waiting on the result of the first multiply, so no news there, but let's turn to that second load. Recall the assumption that on a cache hit, a load will execute in only one cycle. So by the end of cycle 10, that first load brought the cache line holding the data that we need, and now exploiting spatial locality, we would get a cache hit, and so this load would finish by cycle 11. So load 2 is completing its execution. Naturally, we should ask who is waiting to prepare ourselves for the next cycle. So we can see that we'll get a tag match in the reservation stations in mult2. And should we get a tag match in the register file over here? Well, I have another update for you, which is that the third load from the third iteration, which is not shown. In fact, this instruction would dispatch in cycle 11, if you follow along with the previous arguments. So it would allocate a reservation station entry, but R1 is still being computed. The tag is add1, it's not empty, so this time we don't pull the address from the register file directly, but instead use the tag here, and the load would update F0 as we keep seeing. So in fact, we have to update the map table, and now we have the tag of load 3 as the location for the name F0. So back to that question of who is waiting for load 2 in cycle 12, well, we see now that it won't be the register file. As we saw with the first load, which didn't write back to the register file, it looks like the second load also won't write back to the register file. Its value will be passed straight to the reservation station entry that wants to hear about it. Onward to cycle 12. There's no change for the first multiply and store. They are executing and waiting, respectively. But that second load, it finished executing, and so we are in the write back of this load. The CDB is available. There's no structural hazard there. So we broadcast the tag and value on the CDB. So the value is memory at address 76. And just fixing a slight bug in the slides, this should have already had a tag of load 3 for F0. Okay, the CDB is broadcasting, so the reservation station and register file are looking for tag matches. We don't see any in the register file, but if you look back at cycle 11, we would have a tag match on the first operand of mult2. So the reservation station copies the value broadcast over the CDB into that operand field, mem76, clears the tag for QJ, which is sort of shown already, and we deallocate the reservation station entry for that load. And that wraps up the write back of the second load instruction. And by the second half of the cycle, in the issue stage, we realize that both of mult2's operands are now ready. So it's time to issue this multiply to the execute units. So the second multiply issue in cycle 12. Now, if you think about where we are in those hidden instructions, apologies, it's resource constraints of a slide. In the dispatch stage, we are able to pop the third multiply instruction now. But here's the question. Can we actually dispatch this third multiply instruction? So I want you to think about that for a second, possibly pause unless you know the answer. So pause here. And welcome back. If you take a look over here, we have no entries. There is a structural hazard because there are no reservation station entries available. So this means we must stall the dispatch stage. Unlike when an instruction waits in the issue queue in a reservation station entry and instructions can pass around it and execute out of order, this stall, the word stall, implies that this delay, this stalling propagates to younger instructions as well. So we must leave the current instruction at the head of the instruction fetch queue, at the front of the instruction fetch queue. Now, if the instruction fetch queue has ample empty space, this might not be a problem, and the front end can continue to fetch instructions into that queue. But if the instruction fetch queue were full at this point, this stall would propagate all the way to the fetch stage, trying to fetch instructions from the instruction cache. So we'll have to keep an eye out for when we can dispatch this multiply in the future and keep the front end of the pipeline moving along. Okay, on to cycle 13. At this point, both the first and second multiplies are executing, and the first and second stores are waiting for their result. And what you can't see, because our instruction status table is too short, is that the subtract instruction number 3, the third one, has entered right back. And the CDB is available, so we broadcast its tag and value of 72, so that's 80 minus 4 minus 4, over the CDB. If you look back at cycle 12, you'll see that there's a tag match on the register name R1. So we write 72 to R1 in the register file. And moreover, there was a tag match.
So in the last video, we saw the implementation
load 3
of
entry
an
of the
out-of-order
reservation
processor
station
using
entry.
Kamasura's algorithm,
Cycle
including
12,
the details
in fact, this should still say
of the pertinent
busy.
data structures,
So that's just
the
me
actions
updating
taken
the bug
by
there. So given that we got a tag match on add 1 up here in the load 3 entry, then we copy this value into the address field for that load. Now the last reservation station not shown, and the CDB is available, so we broadcast its tag and value of 72, so that's 80 minus 4 minus 4, over the CDB. If you look back at cycle 12, you'll see that there's a tag match on the register name R1. So we write 72 to R1 in the register file. And moreover, there was a tag match on the load 3 entry of the reservation station entry. Go check cycle 12. And in fact, this should still say busy. So that's just me updating a bug there. So given that we got a tag match on add 1 up here in the load 3 entry, then we copy this value into the address field for that load. Now the last reservation station not shown that is waiting for a tag match on this value is the one holding the third branch instruction, and this is what is blocking our load 3 instruction from issuing at this point. Onward to cycle 14. Now looking at the state of our reservation stations, both multiplies are executing and both store instructions are waiting on their results, so they haven't issued yet. Because the third subtract instruction wrote back in the last cycle, then the third branch instruction would have issued. So at this point, the branch instruction number 3 completes its execute, so that its branch has resolved, which implies that the third load can now issue since its operands are available. In cycle 15, finally that first multiply finishes its execution, so mult1 is completing execution. And as foreshadow for cycle 16, let's ask who is waiting on the result of mult1. We can see that the first store instruction will get a tag match, so we'll end up with data flow in this direction. But interestingly, due to the write after write dependence, mult1 will not be written back to the register file in cycle 16. We won't get a tag match there because the tag was overwritten. And we've seen this several times now. Okay, so let's see this in action in cycle 16. The multiply is writing back, so we broadcast its tag on the CDB along with its value. So I'll call that memory at 80 times F2. And we would have had that one tag match with the first store instruction. So this value is copied. Oh, I'll just note, let's just assume that this is holding either the tag or the value. This would be expanded into several entries, so forgive me. So I'll copy memory at 80 times F2 here. And there's no tag match in the register file in the map table. So finally, we deallocate the mult1 reservation station entry, and that wraps up this first multiplies right back. So all of that value copying, we assume that happened in the first half of the cycle, and by the second half of the cycle in the issue stage, the store reservation station recognizes it's now safe to issue the store, and so this first store starts its issue in cycle 16. And the other news in this cycle is that the second multiply has finished its execute. It's 4 cycles of execution. It's now coming to completion. So it finishes its execute at cycle 16 as well. So next to cycle 17. So let's start looking at the write back stage. The second multiply finished its execute. It's in write back. The CDB is available, so we broadcast its tag and value of memory at 76 times F2 over the common data bus. If you refer back to cycle 16, there would be a tag match on store 2. So we copy this value into that field using a shorthand now. and there are no other tag matches on mult2. So we deallocate its entry, and that wraps up its write back. Now looking to the execute stage, that first store issued its cycle 16 last cycle, so it started its execute, and a natural question is how long would that store take? Did it miss or did it hit? Well, for simplicity, let's assume it hit. This is justified. The load before it had a long latency miss, but now we can exploit what's called temporal locality. It should be in the cache. We'll assume with the right permissions, and I'll cover all of those gory cache details in a later module. So for now, we assume it hits, and it's a 1 cycle latency. So by the end of cycle 17, this store's execute is finished. And looking at the issue stage, that second store, by the end of this cycle, its operands, all of its operands are now available because the multiply finished its write back. So that second store issues in cycle 17. Now let's refer back to one of those hidden instructions from the third loop iteration that I hope you haven't forgotten about now. Remember, we had a structural hazard on the reservation stations. This is new for our examples. This is very exciting. So I don't want to assume that simultaneously during write back, while an entry of a reservation station is freed, it could also be allocated at the beginning of dispatch. I'm not sure that the timing would work out there, but we could discuss it in office hours or Q&A. So let's assume that only the cycle after a write back frees a reservation station, then it becomes available to be allocated again. So if you remember, back in cycle 16, we freed mult1, and the third multiply, the multiply from the third loop iteration, it has been stalled in dispatch. It has been holding up the fetch process as well, but now that entry is able to be allocated, and the dispatch of the third multiply can proceed. So the mul number 3 from the loop iteration, structural hazard, is resolved. So we allocate a reservation station entry, we extract its opcode as usual. The multiply reads F0 and F1. So F0, its tag is load 3, so we copy that into the tag bits, and the third multiply also reads F2, whose tag is empty, so we read it from the register file. We've seen all of this before, and it writes to F4, so we have to update the map table to point to mult1, so that later instructions in this loop can find the right value of F4. Onward to cycle 18. That first store instruction finished its execute in the last cycle, so it enters write back now. However, a store instruction doesn't use the CDB. It does not write to any register, it does not output a register value. Now, just as we have read after write, write after read, write after write dependencies on registers, we could have the same such dependencies on memory for instructions that read and write, load and store the same addresses. And this leads to complexity. We will see this in the next module. I'm trying to cover the key ideas of out-of-order execution here. So according to the rules that we've seen so far, this write back of the store is complete in cycle 18. And so we free that reservation station entry. The second store, which issued in the last cycle, it's also starting its execution right now, and with a similar argument as with the first store instruction, let's assume it has a 1 cycle latency due to a cache hit. So it finishes its execute in the cycle as well, or at the end of the cycle. And the other interesting but hidden action going on here is that we can now dispatch the third iteration store instruction. Remember, it was stalled previously. It couldn't dispatch. It was still stuck in the instruction fetch queue due to the structural hazard on that third loop iteration multiply that just resolved in the last cycle. So finally, we can pop that third iteration store instruction from the instruction fetch queue, and we're trying to dispatch it. So we allocate a reservation station entry, and I'm picking store 3 down here simply because I'll assume that you can't allocate a reservation station entry in the same cycle as you freed it, and we just freed store 1 in this cycle. So the third store reads R1, which has an empty tag. So we read the value 72 from the register file. That's the address here, and that is a bug. Sorry, that should say 76. And what is the value that's going to be stored? It's going to come from the register named F4, whose tag is mult1, so we copy that into the tag field. And onto cycle 19, that second store instruction, it enters right back. No need to broadcast on the CDB, as we just saw, so we simply deallocate its entry, and surely some other interesting behavior would be happening with the third loop iteration, the fourth loop iteration, etc. that I'm not showing here. But we filled out our pipeline diagram here, our instruction status table. And so I want to bring your attention, similar to how we ended the last video, take a look at that write back stage. One obvious takeaway is we are achieving out-of-order execution, out-of-order write back in particular for this column. But if you look even deeper, you will notice this example shows us that Tomasulo can overlap loop iterations. Both the first and second loads finished their execute within one cycle of each other. The multiplies were overlapped in their executions. The store instructions were overlapped in their execution and write back. So it looks like I fulfilled the promise at the beginning of the video to give you an example of dynamic instruction scheduling with a larger scope. This is a preview that Tomasulo can achieve a lot of the benefits of static loop unrolling. We can overlap loop iterations and find ourselves a large instruction scope, so long as these hardware queues and buffers are large enough. So why can Tomasulo overlap loop iterations? Well, one crucial feature is its register renaming. So multiple iterations use different physical locations or destinations for registers with the same name. So this feature enables dynamic loop unrolling, combining several loop iterations into a larger instruction scope. Now, the reservation stations buffer old values or old versions of a register name. And crucially, this enables us to avoid write after read stalling. Now, what else do reservation stations enable? Well, they permit out of order issue of independent instructions. So the fact that we have space to buffer an instruction, its opcode, its operands, its tags, enables younger instructions to pass by it without clobbering its instruction state like we had in the 5-stage in-order pipeline. So when we have this space to buffer our instructions until they're ready to issue, this is what enabled us to have out-of-order issue and out-of-order execution. So one other perspective that we saw in this loop-based Tomasulo example is that Tomasulo builds a data flow dependency graph on the fly at runtime. So whereas I've been asking you to note the read after write dependencies in sequences of instructions, that's you building a data flow dependency graph at compile time statically, okay, at lecture time. But by combining register renaming and reservation stations, this algorithm in effect builds a data flow dependency graph connecting the instructions as vertices with edges that represent the necessary flow of data for true data dependency. Now, Tomasulo's scheme offers two major advantages over other pipeline designs. The first is the distribution of hazard detection logic. Now, in contrast, we saw in our 5-stage in-order pipeline centralized hazard detection logic, but here the distributed reservation stations combined with the common data bus, these are what enabled this distribution of hazard detection logic. So if multiple instructions are waiting on one single result, and each of those instructions has its other operand ready, so all of these instructions are only waiting for this one common result, this one common operand, well, because of distributed reservation stations and the CDB, then the instructions can in fact be issued simultaneously by the broadcast or shortly after the broadcast of that result on the CDB. So by distributing the functional units and the corresponding reservation stations, Tomasulo in fact enable true instruction level parallelism, starting the execute of several instructions simultaneously. This is possible with Tomasulo. And the other big advantage over alternate microarchitecture designs is the elimination of stalls for write after write and write after read hazards through the map table, renaming, and the reservation stations. But there's been a lurking challenge, sort of a lurking bug throughout this entire module. I'm going to reveal this bug to you with a story, a little extension of the example that we've been running through. So this is almost an identical copy of cycle 19 from our example, with one big change, which is instead of Z and X being the same array, so the offset from R1 being 0, being equivalent, what if Z was its own separate array located at address, base address of 100 or 104 or something. And now that it's at a different address than the X array, maybe it's on a different page in memory. Okay, I'm assuming very small pages here, but grant me my example, please. What if this first store instruction has a page fault? So take a look at the execute, the write back cycles. Have a think about this, maybe pause. Okay, I'll give you a little hint. So the store executes at cycle 17, where it learns about its page fault. But what about these instructions that come afterward? Well, notice that we have 3 younger instructions. So instructions after this store instruction that have already updated their values. They've either sent these values over the CDB to reservation stations, or even worse, they have written back in the register file. But that violates sequential semantics. Remember that at an instruction that takes an exception, it should appear that all instructions before it have completed and none of the instructions after it have even started executing. That clearly wouldn't be held here. We would not be retaining precise state. So an open question is, how do we recover precise state? So I'm sorry to end the module on such a down note again. I've misled you first with the small instruction scope in the last video, and now you find out that we have a problem with precise state. But I hope you are willing to continue this emotional roller coaster into the next module, Module 5, where we will see how to continue dynamic instruction scheduling out of order execution while retaining precise state and even implementing control speculation. So I'm going to end this video here. In the next short video, I'll do a quick summary of what we've seen in dynamic scheduling so far, the Tomasulo algorithm, and then the video after that, we'll get into dynamic instruction scheduling with speculation. So I'll see you there.